Okay, we talked about the location or measure of location, which is called the percentile, and today we're going to learn about the z-score, which is another way to locate an observation in a distribution. So we have an example. Macy, a 3-year-old female, is 100 centimeters tall. Brody, her 12-year-old brother, is 158 centimeters tall. Obviously, Brody is taller than Macy, but who is taller relatively speaking? That is, relative to other kids of the same ages, who is taller. So according to the Centers for Disease Control and Prevention, the heights of 3-year-old females have a mean of 94.5 centimeters and a standard deviation of 4 centimeters. The mean height for 12-year-old males is 149 centimeters with a standard deviation of 8 centimeters. So Brody is definitely farther above the average than Macy is in an absolute sense. So let me explain what I mean by that. So for Brody, I have 158, which is his height, minus the mean height of 149 centimeters, which it gives us 9 centimeters. So he is 9 centimeters taller than the average 12-year-old boy. Macy, who is 100 centimeters, with the average for 3-year-old girls, 94.5, and that gives us 5.5 centimeters. So you can see that Brody is definitely taller or farther above the average than Macy is, if you just look at it in an absolute sense. But when compared to a typical deviation from the mean, Macy is actually taller. So let me show you what I mean. If I take the 9 centimeters, that's how tall Brody is, or the difference between his height and the average height, over the standard deviation of 8 centimeters for 12-year-old boys, and we get 1.125. Whereas Macy is 5.5 centimeters, and 1 standard deviation for female girls is 4 centimeters. And that gives us 1.375. So this is basically saying that Brody is 1.125 standard deviations above the mean. Macy is 1.375 standard deviations above the mean, meaning that truly Macy is taller relative to other 3-year-old females. So that's pretty much the premise for a z-score. So some questions here. Is being 10 above average a big deal? Well, it absolutely depends on what you're talking about. If you're talking about height in inches, yes. If you're 10 inches taller than someone else, that's a big difference. If you make $10 more per year, then no, it is not a very big difference. Okay? And you'd want to compare it to the mean. It'd just be $10 more. But what is the standard deviation for the yearly salary? That's what we'd be looking at. So we need a way to compare an observation to the population from which it came. So that is what we're going to use a z-score for. So a z-score for an observation, by definition, is the number of standard deviations above or below the mean. Do z-scores have units? No, because I'll show you in the formula in just a second, they cancel out. So what does the sign of a standardized score tell you? It's very important. It tells you whether the observation is above, and if that's the case, you get a positive, or below, and if that's the case, you get a negative, the mean. So the sign is very meaningful. So it's not just in an absolute sense. The sign tells you if it's positive, it's above the mean. If it's negative, it's below the mean. So the formula for this is z is equal to x minus x bar over the standard deviation. So I'll just kind of do Brody real quick here. So Brody was 158 centimeters. The mean height of 12-year-old boys was 149, and then the standard deviation was 8. So when we plug all that in, we get 1.125 was the z-score. So make sure you understand, x is the value of the observation, x bar is the mean of the distribution, and s is the standard deviation. So there are no units because you end up with, for example, here, centimeters divided by centimeters. So they cancel out, so that there are no units. And that is the neat thing about the z-scores. Allow us to compare two different distributions that don't initially have the same scale, for example. So the SAT, if you make a 1600, how does that compare to the ACT? Obviously, you can't even make a 1600 on the ACT. So you could actually compare, say, for example, maybe a 33 is equivalent to a 1600 out of 2400. I'm not really sure, so I'm just making that up. But that's a kind of comparison you could do. You would find the z-scores, and you could actually figure out, did I do better on the SAT or did I do better on the ACT, relatively speaking? All right, let's do a couple more examples. So we have our baseball players who have, over the years, done very well. There's always a debate about who's the best baseball player. So we have some information here. You can read about the home run kings, but the whole thinking or the whole thought process is that maybe it was easier to hit home runs in certain time periods for whatever the reason may be. And that if you had the most home runs like Barry Bonds, doesn't necessarily mean that you're the best. So what we're going to do is we're going to compute all of their z-scores. So I'm going to start with Babe Ruth. And he had 60 home runs. So that's his x value, the actual observation, minus 7.2, which is the average number of home runs. That doesn't sound very good, does it? Divided by the standard deviation of 9.7. So the more variable a distribution is, that's also going to make a difference as to where the observation falls relative to the mean and then the resulting z-score. So when I compute this, I get 5.44. And then I'm going to do Maris next. Okay, so Maris has 61 home runs. The average was 18.8, so it went up that year over the standard deviation of 13.4. For Maris, I get 3.16. So you can already see Babe Ruth is definitely stronger, or has more home runs relative to his time period. Then let's do Mark McGwire. And McGwire has 70. And you want to set up your formula and always say what you're finding is a z-score. So 70 minus 20.7 all over 12.7. And that is going to give us 3.87. And then finally Barry Bonds, who has the most number of home runs, is going to be 73 for his observations, minus 21.4. So you can see as time progressed, definitely the average number of home runs hit in a single season increased. But there's also some changes in the standard deviation as well. So Bonds had 3.91. So even though they all look really good, Babe Ruth, relatively speaking, is the single season home run champ. Okay, so Babe Ruth would have actually been the best relative to the players of his time. So looking at it from another way, in 2001, Arizona Diamondback Mark Grace's home run total had a standardized z-score of negative 0.48. So interpret this value and calculate the number of home runs he hit. So this means that he scored almost 1/2 standard deviations below the mean. So Mark Grace scored almost 1/2 standard deviation below the mean. So he did not do that great. Let's just see what it looks like when we actually compute it. So if I say the z of negative 0.48 is equal to x, which I don't know, that's what I'm trying to find, and he is from the time period 2001, so the average was 21.4, the standard deviation was 13.2, and what I'm going to do is start by multiplying both sides by 13.2. So when I do that, these will cancel. And then, so I'd get this value on the left, and then I would add 21.4. So x is going to actually be 13.2 times negative 0.48, and then you get that value. And basically, that's going to be the number of standard deviations he was below the mean, and then add 21.4. Okay, so when I do that, I get roughly 15.064. So we're going to go with 15 home runs because you can't have anything but whole numbers. So 15 home runs. So when I go back up and look at the distribution from 2001 here, I see that the average was 21.4 and he had 15. So yeah, he was definitely below the average, but it wasn't terrible. He had an okay season, not the best, but that is how you can use the z-score to basically find the relative location, or if you know the relative location, you can find the actual observation value. So that concludes today's lesson, and if you would, make sure to complete homework number 1. And I want to remind you to label all your assignments. So I want to see everything here written at the top of your page. Or if you're starting on the same page, just leave a couple of lines and start the new section. And then make sure to put these in the margin so I can quickly see them when I'm checking your homework. And y'all have a great night.